last video looked at the idea of revisiting pulleys. We had done pulleys once before, but we made sure that those pulleys didn't have any mass, didn't have a moment of inertia of their own. And that made them very simple to work with, really. Now we are going to look at what happens when they do have mass, when they do have moment of inertia. In the intro video for this, I did go through an example of a mass sliding on a table, being pulled down by another mass, and then I threw some friction in there just for flavor. This is going to be pulleys revisited. And the example that I would like to do with this is the Atwood machine. You might remember the Atwood machine from, Unit 2, but the idea was simple. We had a pulley, we had a mass hanging on one side, and we had a mass hanging on the other side. We're going to give this mass 1 could be 10 kilograms, mass 2 can be 20 kilograms, and the mass of the pulley, well, let's give it the in-between. We're going to need a radius of a pulley. Let's call this thing 20 centimeters. And we're going to need what kind of a pulley this is. I know I use a solid cylinder a lot, but a solid disc like this makes a whole lot of sense for using as a pulley, and that counts as a solid cylinder. So it's a good kind of natural, very utilitarian shape to do a lot of these problems with. It doesn't have to be gamma equals a half if you want to do this with a different kind of pulley, and you want to run through this same example with, I don't know, a hollow ball. You can use gamma equals 2/3. You can run through that whole thing. I try and leave the whole problem in terms of gamma and plug in at the end, so you can follow along with your own shape of choice, if you like. So I've got this. I'm going to look at mass 1 and draw a free body diagram for it. Mass 1's going to have M1G pointing down. It's going to have tension 1 pointing up. In the last video I talked about why those tensions are no longer equal, but those are what's going on. I'm going to have to throw a big disclaimer of not to scale, or I'm going to have to make this arrow smaller. Just make this one smaller. And this system, this 20 kilogram block is going to win. So this thing's going to go down, this thing's going to go up. I would like to call up my positive direction here, because in the end that's going to make my acceleration positive, and I kind of like that. So there's mass 1. Mass 2 is also going to have a very similar free body diagram. It's going to have tension 2 pulling up, because that's where the rope is attached. Tension 1, nope. M2G going down. And if this one moving up is positive, then this one moving down has to be positive, because block 1 moving up requires block 2 to move down. Those motions have to be linked. Two free body diagrams down, but now my pulley has mass. So for that, I'm going to need a torque diagram. I have, pulling down on the left side of this, T1, and pulling down on the right side of this, T2. T1 acts at a distance of radius of the pulley, as does T2. Block 1 moves up, block 2 moves down, the pulley rotates clockwise. Those are all positive motions. a particularly math-focused student, someone who is more majoring in math, not just good at math, will want a counterclockwise rotation to be positive. That's just a math convention. I am just telling you it doesn't matter. It doesn't matter which direction we call positive, we just have to stick with one. I like to call positive the direction things are going to move. Mass 1. The sum of forces acting on mass 1 are, I have T1 going up, I have M1G going down, and that's it for my forces, so that equals mass 1 times acceleration. Mass 2. My sum of forces, I have M2G going down, I have T2 going up, and together that equals mass 2 times acceleration. If this thing is going to rotate without slipping, then what I know is that omega is V over R. I have talked about that before, but also alpha is A over R. So I'm going to use this for my third equation. Here comes my third equation. Third equation, I'm looking at the pulley, and I'm not looking at a sum of forces now. I'm looking at a sum of torques because I'm assessing how this thing is rotating. My sum of torques is, I've got T2 times R, that is the torque exerted by rope number 2, and it counts as positive because if that's the only force acting, so ignore this for a moment, this wheel is going to rotate clockwise, which I called my positive direction. Minus T1R, which is negative for exactly the opposite reason, equals, and that's all my torque, so equals I times alpha. I would like to plug in right here that alpha is A over R, so it equals I times A over R. I have 3 equations, and I can work with that. And my moment of inertia is going to be a gamma mr squared. When I multiply that by A over R, one of my r's cancels. So this last equation can become T2R minus T1R equals, right here, gamma m r a. And then I can do one better. I have an r in every term, so I can get rid of those, and this equation can become T2 minus T1 equals gamma m a. So I'm going to get rid of the other versions of this equation. And move this one up here, the already simplified version. And now I have 3 equations with 3 unknowns. I see a positive T1, a negative T1, a positive T2, a negative T2. I would like to take these equations and add them. When I do, the left side becomes T1 minus M1G plus M2G minus T2 plus T2 minus T1. And the right side becomes M1A plus M2A plus gamma ma. I see some things I can do. I've got a positive T1 and a negative T1, a negative T2 and a positive T2, and I've got A in all these terms, so I'm going to factor that side. Left side, I'm going to write this thing first, just because I would rather have the positive thing first. Personal preference. And the right side becomes M1 plus M2 plus gamma M times A. I am solving for the acceleration, so I get M2 minus M1 times G over M1 plus M2 plus gamma M. The top of my equation is my net force, and the bottom of my equation is my effective mass. Now I can plug in some values. And when I plug in all those values, I get an acceleration of 2.7 meters per second squared. And that's pretty good. Let me see what happens if I don't have a mass for my pulley. If I don't have a mass to my pulley, the only thing that changes is this bottom equation. This bottom equation, this would be 0, which means T2 would equal T1. That means this would be 0, and this would be 0, and I would end up with an acceleration of 3.3 meters per second squared. I'm going to undo these scribbles. I would end up with an acceleration of 3.3 meters per second squared. With this situation, with the mass of the pulley not being 0, I get a slower acceleration, which makes sense. The pulley is resisting that rotation at least a little bit, and that is my updated Atwood machine.